Now, in this video, we're going to try to calculate a determinant for a 5 by 5 matrix with row reducing. Now, you can, but there's a bunch of zeros in this matrix, so in principle, you could do some expansions. So for instance, if I were to expand maybe on this last column or on this bottom row or even on the first column, I have a couple of zeros in here. But if I expand this, then I end up with only three matrices, which is good. It's not five, but then I have three 4x4s, and then I might have to expand again, and I have to get 3x3s, and then down to 2x2s. And so you certainly can do the determinants this way, but it's not the most efficient way when you're dealing with very large matrices. Row reducing is better. And the idea, again, is to get it into triangular form. If you could get it into triangular form, then again, you don't need to get the pivots to be one. But if you can get it into triangular form, then you can just multiply on the diagonal to get your matrix, to get your determinant. So that's what we're going to try to do here. So I'm going to start by trying to eliminate everything below this 1 in my first column. And so I'm going to do minus row 1 plus row 3 and put that back into row 3. And then I'm also going to do minus 3 times row 1 and put that in, add that to row 5, and then put that back into row 5. Now, minus 1 plus 1 is 0. Minus 1 plus 0 is minus 1. Minus 1 times 3 is minus 3, plus 4 is 1. 0 doesn't do anything. Minus 1 plus 0 is minus 1. And then in the bottom one, 1 times minus 3 plus positive 3 is 0. This one, I'm going to get minus 3 plus 0 is going to be minus 3. Minus 3 times 3 is 9. Minus 9. Minus 3 times 0, that doesn't do anything. Minus 3 times 3 plus 1 is going to be minus 2. Now, once I have this matrix with this 1, 0, 0, 0, in principle, I could expand now and reduce my matrix to a 4x4. Now, this is going to be equivalent to leaving everything there and continuing to copy out this column and actually get it actually into diagonal form. I do not want to keep recopying this matrix over and over and over again. And so what I'm going to do is I'm simply going to note that if I expand upon this first column, that essentially I'm going to end up with a determinant where I have a 4x4 matrix left behind. And so I'm going to put in my entries here, -2, 1, 2, 0. Again, I'm expanding on this 1 here, this first column, first row. And so what's left is the remaining entries in this bottom part down here. So -1, 1, -2, -1, -1, -1, -3, -1, -3, -9, 1, and -2. And so now we're going to continue by continuing to reduce this now 4x4 matrix. Again, this is not because I have to do this. This is simply because I don't want to keep carrying around this column of values, which is not going to do anything for me. All right, so now let us go from here, and we're going to again do row reducing. Now, I very carefully used these row operations so that I was multiplying a row that I was not replacing in order to ensure that I was not modifying the determinant in any way. So if I had decided to do row 1 minus row 3 and put it back in row 3, that would be equivalent to modifying row 3 by a -1, and that would have modified my determinant. But by modifying row 1, adding it to row 3 and putting it back in row 3 and not row 1, I have ensured that I have not modified my determinant. Now, if I were to swap rows, for instance, then I would modify my determinant by a -1. So I'm going to do that in this case just so that I can get a 1 in my top entry. And then, so this position here, I'm going to do a row operation. Row 1 is going to get replaced with, actually row 1 and row 2, I'm going to swap out. And then I'm actually going to take my new row 1 and I'm going to modify it by a negative, since I have all these negatives here. By multiplying one row by a -1, I'm actually also modifying the determinant by -1. So I can think of this as keeping track of my negatives and my modifications to the determinant by by modifying the determinant both in a way that changes the sign. I've essentially changed it back to the original sign. So I'm going to take my 4x4, and again, that 1 that was up here isn't changing my value at all. And I'm going to swap out row 1 and row 2. So first things first, I'm going to make this -1, 1, -2, and -1. And then from the previous version, this is going to become 2, 1, +2, and 0. So I've done my row swap. And then the second thing I'm going to do is I'm going to apply a negative sign. So this will become 1, -1, 2, and 1. And again, by modifying my determinant by a -1 by switching the rows, and then another -1 by multiplying one row by -1, these negatives will cancel out. This determinant should be the same value as my previous determinant. So now I'm going to do row operations. And again, I'm going to try to eliminate everything below this. So now what row operations am I going to do? I'm going to do 2 times row 1 plus the new row 2. And I'm going to put that back into row 2. And again, because I'm swapping out row 2, I haven't modified row 2 by a multiplier. That doesn't change the determinant. I'm going to add row 1 plus row 3 and then put that back into row 3. Again, I'm not multiplying row 3 by anything, so I haven't changed the determinant. And then 3 times row 1 plus row 4. And I'm going to put that back into row 4. And again, I haven't modified row 4. Now, one thing to kind of keep in mind is if you choose to reduce in another column and you expand on that column, the plus minus things apply. But once you've reduced the matrix and you pulled it out in this case, and I've made my 4x4, the signs all reset. So it's not about where the position was in the original matrix. It's about where it is in the matrix that you're working with. All right, so let's see what happens when I apply these. All right, so 2 times 1 is 2, plus minus 2 is 0. And then 2 times negative 1 is negative 2, plus 1 is going to be negative 1. And then 2 times 2 is 4, plus 2 is 6. And 2 times 1 is 2, plus 0 is 2. Now, row 1 plus row 3, 1 and minus 1 is 0. Negative 1 and negative 1 is negative 2. 2 and negative 3 is negative 1. 1 and negative 1 is 0. And then 3 times 1 plus minus 3 is 0. 3 times negative 1 is negative 3, and negative 9 is negative 12. 3 times 2 is 6, and 1 is 7. And then 3 times 1 is 3, plus negative 2 is 1. And again, I have my 1, 0, 0, 0, and so I'm going to expand on this 1, and I am going to get a 3 by 3 matrix, cross out this column, this row, and I get negative 1, 6, 2, negative 2, negative 1, 0, negative 12, 7, and 1. Great. So now I'm down to a 3 by 3. And so I'm going to do one more set of row operations. And again, I can leave this negative 1 if I want to and maybe try and work with it, or I can tweak it and modify the determinant. And I think just for the sake of simplicity, I'm just going to keep track of the fact that I'm making a change. And I'm going to say negative row 1 goes back to row 1. And again, what I'm keeping track of here is that that's modifying my determinant by a negative. But it'll be more consistent with row operations from other cases where I'm trying to get a 1 in one of these positions. Now I want to eliminate what's below it. So I'm going to say 2 row 1 plus row 2 goes back to row 2, and then 12 row 1 plus row 3 goes back to row 3. So 2 times 1 is 2, plus negative 2 is 0. 2 times negative 6 is negative 12. That's going to get me, plus negative 1 is going to get me negative 13. Negative 2 times 2 is going to get me negative 4, plus 0. And then 12 times 1 is going to give me 12, minus 12 is going to give me 0. And then 12 times negative 6 is going to get me negative 72, I believe. And then add that to 7 is going to get me negative 65. And then 12 times negative 2 is negative 24, plus 1 is going to give me negative 23. And again, now I'm going to expand on this first column. On my 1. And now my 2 by 2 determinant is all I have left. Negative 13, negative 4, negative 65, negative 23. Now, to be consistent with the row reducing process, what I should do at this point is continue with one more row reducing step. Again, I'm going to flip my sign, negative 1, row 1, goes back to row 1. And again, that is a minus sign that will put me back into same value I had to start with. And then I am going to 65 divided by 13 is 5. So I'm going to get rid of 5 times row 1 plus row 2. This is, again, if I'm working in a fully triangular matrix, then this is the last step that I have to do. Now, if I flip my signs here, this will become that, and this will become that. And then 5 times 13 is 65, plus negative 65 gives me a 0. 5 times 4 is 20, plus negative 23 is negative 3. Now, by doing all of this, what is this equivalent to if I had kept all of my columns and rows and everything? If I had kept, after this step, if I had kept all of my my entire matrix all in one place, I would have basically gotten down to a system where, again, my next pivot, I made it a 1, and then I did everything below that. I made this one a 1, and I did everything below that and turned that into 0. And then I made everything down here. Again, I got rid of everything else. I made this one a 0, and then these last two entries were 4 and negative 3. And in fact, what the rest of these ones up top doesn't matter, because if I'm doing my 5 by 5 determinant, when it's in triangular form, I just multiply on the diagonal. 1 times 1 times 1 times 13 times negative 3. And my determinant is going to be negative 39. And same thing for this reduced one. I kept reducing and getting rid of all the stuff that I no longer needed. And if I keep track of all of the sign changes that I made 4 sign changes and no other modifications to my determinant by doing row operations. And 13 times negative 3 is still negative 39. And in fact, if you check, you put the original matrix into a calculator and you do the determinant in the calculator, you get negative 39. So you can do these row operations in order to reduce the matrix. And in fact, this is actually much more efficient than doing the expansion form, because you do fewer operations in order to get the determinant. And again, think about what we would have had to have done originally. So best case scenario, I do maybe expand on this entry right here. They're all 1s. That's great. So that reduces the amount of multiplication I have to do. but then I only reduce this to 4x4 matrices. And then I have to expand on those and do 3x3s, and then expand the 3x3s to do 2x2s so I can finally calculate it. But instead, by doing row operations, I was able to just reduce this to a single 4x4, and then a single 3x3, and then a single 2x2. Whereas if I had done it from up here, I would get three 4x4s. And then again, depending on where the zeros were, I could get as many as four 3x3s from each of those. So now we're up to 12. And then the 3x3s would break out into three more 2x2s. So I would have 36 2x2 matrices um, in the worst case scenario, even given, in fact, there would be 60 if I had had the really worst case scenario and no zeros. And so it's still, that's an awful lot of calculations to calculate, an awful lot of determinants to keep track of, an awful lot of opportunity for losing a minus sign. Certainly much more than doing the row reducing process like this.